Now we're going to talk about the energetics involved in forming solutions. Some solutions release a lot of heat when they dissolve in water. An example there is sodium hydroxide. The container will, depending on how much sodium hydroxide you're dissolving, the container will get hot to the touch. Other compounds, like ammonium nitrate, when they dissolve in water, heat is absorbed from the surroundings and the container gets cold. Let's dig into the energetics behind this. If the total energy cost for breaking attractions between particles is less than the energy released in making the new attractions, the process will be exothermic. So breaking is costing basically steps 1 and 2 here, so separating the solute and separating the solvent molecules. Then when you mix them together, you get this much heat back, and so overall our delta H of solution is net exothermic. So the delta H of the solute, delta H of the solvent, and then the delta H of mixing. Mixing is bigger than the other two combined, so we get a negative delta H of solution. It's an exothermic process. But if it costs more energy to break apart the solute and the solvent than we get back from mixing, depending on what this energy difference is, it might still happen. It's just an endothermic process. So it will pull heat from the surroundings. The solution will get colder because of the net endothermic process. We're going to talk about several different delta H values. And so we are going to combine basically the delta H of the solute and the delta H of the solvent into a term called the heat of hydration. And so our heat of hydration, delta H of hydration, is going to be the heat released when 1 mole of gaseous ions dissolves in water. So our heat of hydration here is going, the delta H of the solution overall is going to be our delta H of hydration, so the amount of energy that it costs to, or that you gain back by combining the water and the ions together, minus the lattice energy, which is the energy that it costs to break apart whatever solid you're looking at and bring it into the gas phase. So let's work through an example. What is the lattice energy of Ki if the delta H of solution is positive 21.5 kilojoules per mole? The delta H of hydration is negative 583 kilojoules per mole. Well, remember on our last slide here, delta H of solution equals delta H of hydration minus the lattice energy. So we can just plug in our numbers. They're in the same units. So 21.5 is equal to negative 583 minus our delta H lattice. And so if I add 21.5 and 583, I get 604.5 is equal to negative delta H lattice. And so negative, and then thinking about sig figs, this one only goes to the ones place. So negative 605 is equal to my lattice energy. All right, solution equilibrium. We've briefly touched on equilibrium before. If we add enough salt to a solution that it is saturated, then we're going to hit a point of equilibrium where if we zoom in, our rate of dissolving our salt and our rate of it recrystallizing are equal to each other. Before that, when it's dissolving, our rate of dissolution is much higher than that of our recrystallization. And remember, at dynamic equilibrium like this, the two processes are still happening on an atomic level, but on the macro level, you don't see a change in concentration anymore. So what is that point where a solution is saturated? That's the solubility limit. It's where the solute and solvent are in dynamic equilibrium. If you add more solute, it's not going to dissolve. And that concentration is going to be dependent on temperature and pressure of gases. If a solution has less solute than that saturation point, it's said to be unsaturated. And solutions can hold sometimes more solute than the saturation point. There we say they are supersaturated, and we'll talk about that in a minute. So how do you make a solution supersaturated? Basically, if you saturate a solution at a high temp and then let it slowly cool down to room temperature, for some solutes, instead of it slowly coming out of solution, they'll get kind of stuck in between the solvent molecules, and we end up at supersaturated. And then they are unstable, and so once you do something to disturb that supersaturated solution, you will lose all the solute above the saturation point. So an example there is shaking a carbonated beverage. You will quickly lose all of your carbonation. One common demonstration to see this is sodium acetate. So sodium acetate can be made into a supersaturated solution. So here, this solution contains more sodium and acetate than it can hold. And if you disturb it by adding just a single crystal, all of a sudden all of the extra will come crashing out of solution. We can look at a graph like this and look at solubility curves where we can see as generally as our temperature increases, so does our solubility. So we can look at sodium chloride here. As we increase in temperature, we can get a little bit more sodium chloride into solution. It's more dramatic for some other salts. Look here at potassium nitrate. Your solubility goes way up as you increase the temperature. Sodium sulfate here is kind of the opposite. It becomes less soluble as you increase the temperature. Okay, so let's practice using these solubility curves. Decide if each of the following solutions is saturated, unsaturated, or supersaturated. So I would recommend pausing the video and working these through yourself and then checking your answers. So 50 grams of potassium nitrate and 100 grams of water at 34 degrees Celsius. Notice our axis here is grams of salt and 100 grams of water. So we're going to be at 50 grams here and 34 degrees Celsius. And we are looking at potassium nitrate, which is the red one there. So if we're right there and at 50, we are going to be right at the saturated point. 50 grams of potassium nitrate and 100 grams of water at 50 degrees Celsius. So there's my 50, bloop. We're way over here, again looking at this line, so we're going to be unsaturated at that point. 50 grams of, again, potassium nitrate in 50 grams of water, which means if we convert it to 100 grams of water, that's going to be 100 grams in 100 grams, which we have to do because our axis here is defined as the 100 grams. So we're up here at 100, at 50 degrees Celsius, we're right there, and so we would be super saturated. Then 100 grams of ammonium chloride in 200 grams of water, so that's going to be 50 grams in 100 grams at 70 degrees Celsius. So here's my 50, here's my 70, and I'm looking at this blue one. So I am under the line, so I'm unsaturated there. And then my last one, 100 grams of ammonium chloride in 150 grams of water. So in 100 grams, that's going to be 75 grams NH4Cl at 50 degrees Celsius. So 75 is right here, 50 is here, and we're going to be above the blue line, and so that's going to be super saturated. So check our answers: saturated, unsaturated, supersaturated, unsaturated, supersaturated, which is what I had.